Have you ever bought a tool for some job around the house and it's just completely wrong for the task?
Oh, all the time.
But you keep it, right? You throw it in the garage, and then, I don't know, years later, you realize it's the only thing that works for some new project you hadn't even thought of yet.
I mean, that's pretty much the life story of the equation we're talking about today, isn't it?
It is a classic happy accident. Today, we're diving into some physics papers from way back in 1926. We've got Schrödinger, Klein-Gordon, and we're looking at how an equation that was seen as a failure for, 80 years?
At least.
Ended up becoming basically the prophet of modern particle physics.
It's a great story about how being wrong is sometimes just being right about a question nobody's asking yet.
Okay, so let's set the scene. Mid-1920s, quantum mechanics is exploding. Erwin Schrödinger releases his famous wave equation. It's brilliant.
Absolutely revolutionary.
But it had this blind spot. It was non-relativistic.
It completely ignored Einstein. See, Schrödinger's math, it treated time and space as totally separate things. In his equation, time is first order, but space is second order. They're not on equal footing.
And Einstein's whole thing with special relativity is that time and space are partners. They're woven together.
Exactly. So Schrödinger's equation was great for, slow physics.
But it couldn't handle particles getting anywhere near the speed of light.
Right. So almost right away, you have these physicists, Oscar Klein, Walter Gordon, and Vladimir Fock working on his own. They decided to force the math to cooperate.
They wanted an equation where time and space were treated exactly the same.
They took Einstein's energy-momentum relation, the famous E squared equals P squared C squared plus M squared C to the fourth.
The big one.
And they basically baked that directly into a new wave equation. The result was the Klein-Gordon equation. It was elegant, symmetrical.
And it put space and time on equal footing.
Perfect equals.
But this is where that tool in the garage thing comes in. They build this beautiful relativistic equation, and they immediately try to use it on the electron.
Yeah.
It just didn't work. Looking at the data from back then, the predictions for the hydrogen atom were just off.
Off is putting very politely. Yeah. It completely failed to predict the fine structure of the atom's energy levels. The patterns were all wrong.
And the culprit was spin, right?
Yeah, spin. The Klein-Gordon equation is for a particle with zero spin, a scalar particle. But electrons are spin 12.
So you can't describe a spinning top with math that's designed for a perfectly smooth stationary ball.
You can't. So Paul Dirac comes along, writes his own equation, which does account for spin, and boom, everyone moves on. Klein-Gordon gets put on a shelf. Historical footnote.
A classic case of the right tool for the wrong job. Which, actually brings us to our sponsor, Embersilk.
A very smooth transition.
Well, because in business, you can't just throw a generic solution at a really specific problem. If you're looking into AI for training or automation or custom software agents, you need the precise tool. You don't want a spin zero solution for your spin 12 business challenge.
I like that.
So check out embersilk.com to see where AI agents could actually make an impact for you.
All right, so back to our equation on the shelf. It's just sitting there for decades.
Decades. Until the standard model of particle physics really starts taking shape. And physicists realize that while particles like electrons have spin, there should, theoretically, be particles that don't.
Scalar fields.
Which is exactly what the Klein-Gordon equation describes.
It describes spin zero particles. The problem was, for a very long time, we'd never actually seen a fundamental particle with zero spin. It was all just theory.
Until July 4th, 2012.
Ah, yes. CERN.
The discovery of the Higgs boson.
And the Higgs is the first fundamental elementary particle we have ever found that has zero spin.
So all of a sudden, this failed equation from 1926 is the only math on the books that can accurately describe one of the biggest discoveries of our lifetime.
It fit perfectly. And there's another really cool layer here. Schrödinger's equation gives you a probability, but Klein-Gordon gives you something that could be interpreted as charge density.
Which means it allows for both positive and negative charge.
Exactly. It naturally sort of predicts the existence of antiparticles matter and antimatter long before we really had a handle on what those even were.
So it wasn't a dead end. It was just a prophecy. It was sitting there waiting in the textbooks for us to finally build a machine powerful enough to find the particle it was always meant for.
That's the beauty of it. No good, rigorous work is ever really wasted in science. Sometimes the theory is just way ahead of the experiments.
It really makes you wonder, what other discarded ideas are sitting on a shelf today, just waiting for their moment.
Waiting for us to catch up.
If you enjoyed this deep dive, make sure you subscribe to Intellectually Curious. And hey, if you learned something, please leave us a 5-star review. It really does help spread the optimism. Thanks for tuning in.